All right, today in this video, we're looking at different aspects of hypothesis testing. So for example, determining if a set of data is normally distributed. We're going to be calculating critical values and p-values, as well as actually performing a hypothesis test with some set of exercises. And we'll be doing this on Excel, and we'll type the responses and copy paste any results into Word. So on the left side are the exercises that we're doing. There's 4 exercises. The first exercise is asking you to determine if the following data is normally distributed. And so on the bottom of this, on the bottom right corner of this Excel, I have the various exercises labeled for different worksheets. And if you'd like to add a worksheet, you just click on this plus icon and then rename the worksheet by double clicking on the label and label it whatever you want. Okay. And if you want to delete it, you can right click it and delete the sheet. All right, so I have all the sheets labeled for my exercises. And for the first exercise, I've typed in all the data into one column. So now what we want to do is we want to determine if it's normally distributed. So we're going to do a scatter plot. We call this a quantile plot. So what we want to do is we want to essentially start a column that is labeled count. This is what I call it. And this is just a set of numbers used for the formula that we will use to calculate the quantiles and the z-scores. Okay, so what I do is actually before I even start the count, what you want to do is in the first column, you want to highlight all of your data. Then you want to sort the data in order from smallest to largest. So highlight all of your data. You want to go to the data tab here, and you want to go to sort. So you want to sort from smallest to largest. Continue with the current selection, and then sort your data from smallest to largest. You want to do this step before you go any farther, so that way your quantile plot is correctly displayed. So now you want to go ahead and start with your count by starting with odd numbers. So count from 1 and on using odd numbers, so 1, 3, 5, 7. Then since we want to use shortcuts here and not have to type in so many numbers, you want to highlight the numbers, hover over the bottom right corner of the cell, of the last cell, and then double click on it or drag it. So you can click, hold, and drag it as so, or you can double click on it and it will shortcut count all of the numbers for you. All right, so like I said, we needed this column in order to calculate the z-score in the quantiles. So this is going to be the z-score for this column. And what we want to do is essentially we want to divide the data. We want to divide the data into essentially 70 pieces. Since we have 70 numbers, we want to divide the data into 70 pieces for the quantiles, and then we want to essentially calculate the z-score in each quantile region. So what we're going to do to calculate the z-score, you're going to be using the function known as, and I'll zoom in here so you guys can see that. So the function is norm.s.inverse, and this function returns the z-score for a normal distribution. So then we're going to go ahead and open the parentheses, and now it's asking for a probability. So you're going to calculate this probability using the following formula. So the formula for the probability is you take your count, so you click on that cell, divided by parentheses. So you want to divide by twice your sample size. So my sample size here is 35. Since I have a total of 35 data numbers here. Close the parentheses one more time. So essentially what this does is it breaks your data up into like the chunks that I said, 70 pieces, and then you're evaluating the z-score in the midpoint of each piece. So like for example, if you have 0, your first number is 0, then 1, 2, 3, all the way to 72, right? So ... And you're saying, okay, well, I'm looking at the midpoint of each like set. So I want to evaluate the z-score here, you know, get it there, and get it for every single odd number. That way it's sort of like the midpoint between two numbers. And that's essentially what we're doing. And then we're taking those z-scores and we're using it to display on the scatter plot. So then we click on the z-score, we go hover to the bottom right corner, and we double click on it for the shortcut. All right, now we want to go to insert. Since we want to insert a chart, we want to go to display the scatter plot. The first option is fine. Now, if you have data already displayed in this chart, what you want to do is you want to delete all of the data there. You don't want any data that is pre-selected by Excel, because it's most likely going to be incorrect. So you want to go to select data, and if there are any entries here, you want to delete them by clicking on this remove icon, or just literally deleting everything using the delete key. All right, so now since there's nothing here, I'm going to go ahead and add an entry. You want to go to series X value since you want to select your X data. Now we're graphing z-score versus data. So the data is my x-axis. All right, then you want to click on your y values. By default, this is labeled 1, but you want to delete that. Then you want to go ahead and select your z-scores for your y-axis. All right, so now you should have a nice looking graph. Now remember, I said that this graph will probably look funny if the data is not sorted from smallest to largest. So make sure that you do that before you even get to this step. All right, so hit OK for both tables. And now you have a nice looking scatter plot with z-score versus the data. Now, if this data follows a straight line, then we can say that the data is approximately normally distributed. So it looks like it's in a straight line pretty much for the most part. So how do we determine how much of a straight line it follows? Well, we want to go to the top icon here, this plus icon, and if you don't see that, you can use the add chart element icon here. But regardless of whichever you choose, you're going to go to trend line and then go to more trend line options. If you use this, then you're going to do the same thing. You're just going to go to trend line, more trend line options, more options here. You should see a table pop up on the right, and you want to go to display R squared value. Make sure that linear is selected for the trend line because you want a linear trend line. You want to see if it follows a straight line. You can exit out of this, and you should get a nice little trend line. And it says that the R squared value is 0.984. Remember that if the R value is close to 1, this means that it follows a straight line. So what we could do is, technically this is the R squared value. You can find the R value by taking the square root of that number. So if you want the square root of that number, all you have to do is do equals SQRT and then type that number in. And that gives you a R value of 0.991. All right, most of the time you don't need to do this is because, you know, if the R squared value is high, this means the R value is also going to be high. However, if you want to double check just to make sure that it's close to 1, then you can do this method. All right, so the R is the correlation coefficient, and then the R squared is the coefficient of determination. All right, so now that we know how to do this, make sure that you label your charts. You know, give it a title, you know, whatever title that may be. In this problem, we're just looking at some random data. So we're doing a essentially a normal quantile plot. For determination of, you know, normal distributed, if it's normally distributed. And then for the y-axis, if you want to label the y-axis, you can do add chart element, or you can use this plus icon, and it'll give you the various axis titles. You just click on that, and then just label this. This will be the z-score. And then in this example, they just gave us a bunch of data, so we'll just say data. If they give you heights, then you make sure you label a height, for example. All right, and then once we have this, what we can do is we can put these results in number one. So we want to show our data table here. All right, so since we want to show our data table, I'm going to essentially just copy paste my table as well as my graph. So this is my table. I'm going to select it. You can right click and copy if you like. All right, select my table, show my data, and then you can click, you know, right click, copy this, or Control X, whichever the case may be, and then you can paste the data, the graph as well. Okay, however way you like to do it, it's fine as long as all the results are there. And then for number two, we want to find the critical value for the following. We want to draw a diagram labeling the critical values in the critical regions. All right, so then what we want to do is we want to determine if we're using a z-test or a t-test here. So let's go to exercise 2. Now we are looking at n equals 50, and our level of significance is 0.02, and we're looking at a two-tailed test. All right, so then that means that if we're looking at n equals 50, we're looking at a z-test, right? Since n is greater than 30. So if the sample size is greater than 30, you're going to use a z-test. So in order to find the critical value, z-crit, you're going to be using the formula, let me say z-crit equals, and then we'll start here. So then you're going to do equals, and then you're going to be using the norm.s.inverse function that we used last time, and you're going to give it a probability. So you're going to give it the alpha, now the level of significance. Now since this is a two-tailed test, right, this means that you're going to be looking at a positive and a negative critical value. So, and also what you want to do is you want to take the alpha and divide it by 2, right? So what we're going to do is we're going to take the alpha, the level of significance, divided by 2. And this will give us our left tail. If we want the right tail, then we do 1 minus this number. Okay, so this is going to be for the left side. And if we want the right side, we do the same thing, but 1 minus. So we do the 0.02 divided by 2, but 1 minus, and that will give us the right side. And notice that we have 2 critical values, and they're the same thing, but plus or minus. Okay, this will always be the case for a two-tailed test. You're going to have 2 critical values, 1 positive, 1 negative. If they wanted just a left-tailed test, you would just use this guy. Right-tailed test, just this guy by itself. All right, that concludes exercise 2A. So let me just go ahead and label this. This is 2A. Now I'm going to do 2B. So it says n equals 15. Level of significance is 0.10. And we're looking at right-tailed test. So since n equals 15 is less than 30, I'm using a t-test. And this, which means I need a t critical value. All right, so to do a t critical value, you're going to be using the t.inverse function. Now, if it's a one-tailed test, you just use the t.inv. And I'll make this a little larger so you can see what I'm talking about. So t dot in, down here there's a t dot in 2t, but if we're just doing a one tail, just leave it like that. We're doing a right tail test, so you're going to do, remember, if you're doing the left side, you're going to be doing just alpha. If you're doing the right side, you're going to do 1 minus alpha. Okay, so since we're doing a right tail test, we're going to do 1 minus the level of significance, comma, and then your degree of freedom. We got to calculate that. And that's simple to do. Just take your n, your sample size, take away 1. All right, so again, repeating, if you're doing a left tail test, just do 0.10. If you're doing a right tail test, do 1 minus 0.10. If you're doing a two-tailed test with this function, then you could do the alpha divided by 2, just like we did for the z test, and then do 1 minus and then the regular. So there's a couple different ways you can approach this. All right, so we're going to go ahead and enter. This is our right-tailed test critical value. All right, so now let's look at 2c. And for 2c, our n is 10. Our level of significance is 0.01. And we're looking at a two-tailed test. All right, so now, here I'm going to make this a little larger. All right, so now our n equals 10, so we're doing a t-test. We need our t-critical. So you could use the t.inverse.2t function. And in this case, they're just looking for the probability. So you could, what we're going to do is we're going to double check this. Okay, so since you're doing a two-tailed test here, you can just type in the probability and then the degree of freedom, which is 10 minus 1. Okay, and I'm going to double check this. Okay, so we get this value as the t critical. Now, if you were to use the t inverse function without the 2t, it should still work. You just have to keep in mind that, let's see, so if we were to do t dot inverse, you would have to do, alpha divided by 2, and then you'd have to do, so we'll do alpha divided by 2 for two tails, and then 10 minus 1, and then you'll get the negative version, and then you would repeat this for 1 minus alpha divided by 2, and then the degree of freedom, and that will give you the positive version. So you can either use the regular inverse function, remember to divide by 2, or you can use the two-tailed version, and then you don't have to divide by 2. But if you use the two-tailed version, then you just have to do both sides, so you have to do 1 minus 0.01, so that you can get the negative and positive version. Oops, this is not even right. So yeah, this function will not give you the left version, so then you're going to have to do the negative version of that, so negative that. Okay, but just keep in mind that you should have two critical values since you have a two-tailed test. All right, so those are a couple ways of doing it. All right, so now let's look at exercise 3. We want to find the p-value. Okay, so since we want to find the p-value, let's go ahead and label this 3a. Z is negative 0.23. And we're looking at left tail test. So since we're obviously looking at z, we're using a z-test here. So we need to find the p-value from a z-test, from a left-tailed z-test. So to find the p-value, we use the function equals, and then we use norm.s.distribution, D-I-S-T, parentheses. And this gives us the probability given a z-score. So what we need to do is we need to calculate the probability for this z-score. So I'm going to just click that z-score. Actually, I'm just going to type it in, negative 0.23. comma, and then this will always be true. You will always use true for cumulative if you're doing the probability, the cumulative probability. So this gives you the value from the left side. And since we're doing a left-tailed test, this is perfectly fine. However, if you're looking for a right-tailed test and you need the right side, you need to do 1 minus, okay? The entire distribution adds up to 1. So if you want the left side, just leave it like that. If you want the right side, you do 1 minus. Go ahead and enter, and this gives you your p-value for that that specific test value. Oh, one other thing that we need to do is I need to copy paste the results, but I also have to show you how to draw a diagram labeling the critical value in the critical regions. So in order to do that, there's a couple ways you can go about doing it. This is just an artistic freedom that you have, but one way that I like to do it is to use Microsoft Paint. And then what I do is I copy paste an image onto Paint, and then I edit that image on here. So I search on Google for an image of a normal distribution. So go to image, and I select an image. I copy the image. I go to Paint, and I paste it there. And then you can edit this however way you like. So I'm going to get rid of this because I don't want those numbers. And I'm going to use the paint bucket in order to color this so that it's clear. But it's up to you how you want to do this. And then you can do a paintbrush, and you want to or you can use a line, and you can label your lines on here. So for number 2, part A, we had a critical value of negative 2.32 and 2.32. So I'm going to label that around here, 2.32. And negative 2.32. And then we want to shade both sides. So what I'm going to do is I'm just going to do another line there, another line here. And then I'm going to use a paint bucket to kind of color that region in, just like that. And then I'm going to use the font icon, and I'm just going to type in, that's my critical value. So my critical value was negative 2.32 and 2.32. All right, so that's just one easy way of doing it that I found that was simple, straightforward, using editing tools. And then you can, select the image, copy, paste it onto your document. So this will be for part A. And you have a nice, lovely image of, your two-tailed test here. All right, so I just wanted to mention that. So that's something that you can do. Now going back to our p-value. So we want to do so for exercise 3, let's go ahead and go to 3B. Our z is 0.85, and we're looking at a two-tailed test. So we need to find the p-value. So we're going to use the same function for the z, norm.s.dist. Type in your z-score. Now, since you're looking at a two-tailed test, you have essentially two values that you want to look this up for. So since you're looking at a two-tailed test, you can do the negative version of the z, or you can do the positive version of the z. So actually what we want to do is the negative version of the z, because we want the area to the left. So what I'm going to do is I'm going to do the negative version of the z. So when you use this function for a two-tailed test and they give you a positive z, just make it negative. If they give you a negative z, then just leave it. All right, so negative z, comma, and then true. If you enter, you'll get the correct p-value. Now, the reason why you're going to do the negative is because if you look at this graph here, it's only looking at the area to the left, which is this red region. So if they give you like a z that is positive, like this positive 2.32, and you use the function, it's going to give you the area to the left, which is a large area, and that's not what you want. You want the small area to the left here, or the small area to the right. So if you were to use the positive version like this and say true, oops, this is the wrong function. So if you were to use the positive z and say true, then you got to remember that, okay, well, that gives me a large area. I need to do 1 minus to get this small area to the right. And that will give me the same value. Okay? And that's how you were to do it if you wanted to do a right-tailed test, you would do this. Okay? If you were to do a left-tailed test, so I'm going to just go ahead and label that, and I'm just going to say right-tailed test. And this here would be a left-tailed test, which would be this. Now, since we're doing a two-tailed, right, we're going to have to double our results here. So I'm going to double the results that I get for my z. So, which is, I can use either function, doesn't really matter. So I'm going to double it and I get this answer. So this answer is my answer for the p-value here, because we're looking at a two-tailed test. Okay, but I wanted to show you how to do it for the various tests. So that's my answer for 3b. Now let's go to 3c. All right, so 3c, we're looking at a t-score 2.585, and it's 15, and we're looking at a right-tailed test. So since we're doing a t-score, we're looking at a t-test, so we need to calculate the degree of freedom, which is 14, 15 minus 1. So pretty straightforward there. So now we need to do the p-value. And I'm going to show you how to do this for left-tailed, right-tailed, and two-tailed. So let's do the left-tailed first. If we're doing the p-value for the t, you're going to do the t.dist function, and this gives you the p-value to the left. And then you're going to type in your t-score, your degree of freedom, which is 15 minus 1, and then you're going to type in true. And this will give you your p-value. Let's see here. Sorry. So if this were a left-tailed test, you need this to be negative 2.585. Okay, so if this were a left-tailed test, this is going to be a negative number for the p-value. If you wanted to find the left, if you wanted to find the area to the left, even though it's a positive t, you would just do 1 minus. But normally they will give you the left side, which is a negative number. So you would do this for the left, okay, if it was a negative 2.585. And then if you were doing, oops, this is the wrong function. If you were doing the right side, right tail, then you would type in your z, and then 15 minus 1, your degree of freedom. So that's if you're doing a right tail test. And then you get the same number, you know, because the p-value is the same for both sides. And then if you're doing a two-tail test, which is what we're doing, we use the .2t function, and then type in our z-score, and then 15 minus 1. All right, and then we can double that value, because that's what we want to do. We want to double that value, which they actually already do for us. So see, if we double that value, we get 0.216, and that's for the two-tailed test. So the t is nice because it already doubles the p-value for you because it's a two-tailed function. So there's no need to double the p-value. All right, and this right here is my final answer for the problem. All right, if we look at 3D, we have a t-value of negative 1.375, n equals 28, and two-tailed. All right, so then we want to do the p-value. So equals, and then type in your function. And we want a two-tailed test, or, oh, actually, I'm sorry, guys. 3D was a two-tailed test, so this is not the answer to that. Apologize. We want to do a right-tailed test, so this will be the answer. There you go. This one, they want a two-tailed test. All right, so then we want equals t.dist.2t. Now, I believe that this function will not accept negative values. So I'm going to try typing it in. It should not take in negative values as far as I remember. It will give you an error because it's looking for a positive value and not a negative value. So what you can do is just make it positive because you're doing a two-tailed test anyway, so you have both positive and negative versions. So then we have, you know, the actual p-value for the two-tailed. All right. So it's just an error with this. It's just a issue with this function is that it only takes positive values for this part here. All right, that's your p-value for the two-tailed test. All right, so now let's go ahead. We're going to exercise 4, and we're going to do a full-fledged hypothesis test here. All right, so we have a random sample of stipends of teaching assistants in economics is listed. So is there sufficient evidence at the alpha equals 0.05 level to conclude that the average stipend differs from $15,000? The stipends listed in dollars are for the academic year. So they give you a bunch of stipends, seems to be about 12 of them. And I went ahead and I typed in the results into Excel, and those are my stipends, and there's 12 of them. And what I want to do is I want to calculate the average of these stipends and the standard deviation. So I'm going to go ahead and calculate the sample mean, which we call X bar. So this is my X bar. And we're gonna calculate the average, so equals average. And then select your numbers, close the parentheses, and enter. So that's my average stipend. And we want the standard deviation, which we label S. So I'm just going to call it S for standard deviation. And so you're going to do equals STDEV dot S, since we want sample standard deviation. Parentheses, select your numbers, close the parentheses, and enter. So this is your sample standard deviation. All right, we're going to need those numbers later, so we're going to keep those tucked away. So now we're going to go through the entire hypothesis testing process. So what we need to do, I'm going to make this a little smaller here. So what we want to do is we want to start with step 1. So step 1, we're actually doing, so since the sample size is 12, we're using a z-test. So we're gonna say, or t-test, I'm sorry, t-test, since our n is less than 30. Our sample size is 12. All right, so then what we want to do is we want step 1, and I'm going to temporarily make this larger so that we can focus on the word. All right, so then step one is to set up your hypothesis. So so you write your hypotheses and identify your claim. So this is step one in the hypothesis testing process. So if you're not comfortable, if you don't remember the process, we're going to be kind of identifying the steps here. And then if you want to do, we want to type in our H0 and HA. H0 is for our null hypothesis. So we're going to go to insert, and we're going to go to equation, and then this will help us write some symbols. So we have H sub 0, so H underscore 0, and then you can space colon, and then that will bring the number to the bottom. And then if you want to do mu, is /mu. So what we want to do is we want to set up a hypothesis, and what we see is that is there sufficient evidence to conclude that the average stipend differs from 15,000? So the claim is that the average stipend is 15,000. So the claim, or the hypothesis, is that mu is $15,000, but HA is not equal to $5,000. So the mu, and you can use the does not equal to symbol over here, $15,000. So this right here is our claim according to the problem. So step one is done. We identified our claim from the problem and our hypothesis. So step two is to find the critical value. So you may remember that we did this in Excel in the previous step. So this is what we're going to do in Excel. But step two, we want to find the critical value using Excel. So what we want to do is our alpha is 0.05 and our n is 12. So we're going to go into Excel real quick and focus on that. So we said that our n is equal to 12. I'll just write it like this, n is 12. So that means our degree of freedom is 11. So let's do our critical value. So we need T critical. So and remember, to find the critical value, you do T dot inverse. And we are looking at if you go back to the hypothesis, if the hypothesis does not equal to for the alternative, this means we're doing a two-tailed test. If it's greater than for the HA, it's a right-tailed test. If it's less than, it's a left-tailed test. So now that we know we're doing a two-tailed test, we can go ahead and we can probably just go ahead and use the two-tailed test version. But I'm just going to use the regular the regular inverse function here. So what we do is we want to do the alpha divided by 2. So let me label that real quick. So my level of significance is 0.05. I believe that's what it says. Yes, 0.05. So then we can find our T crit, so equals T dot inverse. So we're going to take our alpha and divide it by 2. And then calculate our degree of freedom, 12 minus 1. That gives us our negative score. And we want to also do our positive score. So T dot inverse 1 minus alpha divided by 2, since we want the left side, or the right side, I mean, and then 12 minus 1. And that gives us both our critical values. All right, so then what we ended up doing, right, for this, we said that our critical value, so T sub C equals plus or minus. If you want to do plus or minus, you can type in plus and then minus right away, and it'll do it for you. 2.201. So around there. So that's our critical value. So step 3 is to find the test value. And I'll go ahead and type that formula in so that you guys, so that you know what we're talking about. So the formula for the t-test is this guy. So I'm going to type it in. So we're going to do the equation editor, insert equation, and then the formula for the t-test is, so if you want to do a fraction, you do a slash and then space. And then we want to do the x bar. So to do the x bar, let me zoom in, focus on this here. To do the x bar, you want to click on this icon, accent, and then here. So we want x bar minus our mu divided by s divided by square root. So we can say forward slash sqrt of n. So this is the formula for the t-test. You can also do square roots in here if you don't know how to do that, okay? And then it'll do it for you. You can also do fractions here and subscripts. So this is the formula that we want to use. So we're going to calculate this on Excel. But before we do that, we're going to plug in the numbers. So we know that x bar is is that number, 14,347. So we're going to type that up. Minus mu, our mu is our hypothesis, so 15,000. Divided by our s we found on Excel. And to do, we want to do the square root of 12. Okay, and then we're going to say this is approximately equal to, you can use this approximately symbol. And then we'll calculate what that is on Excel. All right, so we're going to go ahead and move on to Excel, and we're going to calculate our t-test. So to do that, we're going to say equals, parentheses. We can type in our number for x bar minus mu, close parentheses, divided by, open parentheses, s divided by square root. To do the square root on Excel, sqrt, parentheses, 12, close the square root parentheses, close the denominator parentheses. And there's our function. We can go ahead and enter, and we get our t-test, negative 1.10. 104. All right, so now what we're going to do is we're going to label a diagram for this scenario with these two sets of values. All right, so then again, going back to the paint example that we had before I did all this stuff here. So let me zoom in on that. Okay, so now I want to label my criticals here and my t-test. So I'm going to label the criticals first, 2.201. And I'll label those in red. And I don't want the lines to be so thick, so I'm going to go to size and do a thin line. All right, 2.201 right there. And then negative version like that. And then I want to shade the two tails because since it is a two-tailed test. So I'm going to do a little line here just to kind of cover that off. Do a little line here to cover that off. And then I'm going to use a paint bucket and shade it red. All right. So now we got our two-tailed here. And I need to label my critical value, so I'll label that. 2.201. or negative. Okay, so now we got our critical regions. Now we're going to label our t-test, which we said was negative 1.104. I'm going to do that in blue. It was negative, so we're going to go over here. Right. Go to our font. And that's my t-test. All right, so this is the diagram of the scenario. So now, as we can see, we are not in our rejection regions. Okay, so if you see here, that's my rejection region there in red, and so is this. So since this 1.104 is not in the rejection region, this means that we do not reject the null hypothesis. So we fail to reject here. If this were located inside the rejection region, we would reject. Now I'm going to go ahead and select this diagram, and I'm going to go ahead and copy paste it into my report, and I'm going to just make it smaller. It doesn't have to be that big. And now we have our guy. So now step 4. Step 4 in the process is to make a decision. Now I already mentioned that we can already make a decision here because we know that it's not in the critical region, right? So the test value is not in the rejection region, so we fail to reject the null hypothesis. Also, before we even get to step 4, I want to show you how to do the p-value, just in case they ask for a p-value. So to calculate the p-value, again, remember we want to do a t-test. So let's go ahead and do the p-value real quick. So if you want to do p-value, we go to t.dist. And so since we're doing a two-tailed test, we're going to do 2t. Type in your test value, but remember that the test value is negative here, so we're going to make it positive, comma, then your degree of freedom, 12 minus 1. All right, and there's our p-value, 0.2932. If you don't like using the two-tailed test, the two-tailed version, you can go to just use the one-tailed version as well. And then just remember to make sure that the t-test is negative, which it is here, so you're fine. And then you can do your degree of freedom. And then, oops, we're missing something here. I forgot to do true. And then you can double that value. This is the wrong number. And then you can double that value to get that one. So there's a couple ways to do it. But we got the p-value, 0.2932, so we're going to report that. And you may recall that if this number is bigger than our alpha, then we fail to reject. So this number is indeed bigger than alpha because our alpha is 0.05. All right, so then we say that we fail to reject, so we can also say the p-value is greater than our alpha. If you want to type in alpha, you go to equation editor /alpha. So we fail to reject. All right, so there's a couple ways to make a decision here: p-value method or traditional method, which is critical values. So step 5, summarize the results. So if you want to summarize the results, well, since we failed to reject, that means that we have no evidence. So we don't have enough evidence. So there is not enough evidence at the 5% level of significance. And in this case, what we were trying to do is we were trying to reject the claim because our claim belongs to our null. Remember, the goal of hypothesis testing is to reject the null hypothesis and to accept or support, essentially, you want to support the alternative. So since the claim belongs to our null and we're trying to reject our null, this means we're trying to reject our claim. If our claim belongs to our alternative, this means that since we want to support the alternative, that means we'll support the claim. In this case, since the claim belongs to our null, we will reject the claim. So there is not enough evidence at the 5% level to reject the claim that, and then the claim goes back to the original claim of the problem, which is the stipend. So the claim was that the average stipend of teaching assistants in economics is $15,000. All right, and that's our summary of our results. So that's going through the entire hypothesis testing process and the different aspects of that process. So I hope you guys found this useful. This is, like I said, just one of the ways that you could do the test. There are a bunch of ways that you can do this, but this is using the tools of Excel in order to do the job. All right, guys, take care. Have a great day.